secant function the same way. Remember that cosine starts and stops on the amplitude. Let's go ahead and label our axes first though. Starts and stops on the amplitude, halfway through it crosses zero, or goes down to the amplitude, and then it goes there for on the intercepts at the quarter and, or excuse me, the pi over 2 and the 3 pi over 2. All right, remember that secant is the reciprocal of cosine, so just like with cosecant and sine, there is an asymptote at every intercept of the original cosine function. That means that we put our asymptotes here, here, and here. Now instead of it being at every pi, the intercepts of secant occur at every pi over 2, skipping the integer values of pi. So let's go ahead and mark out our extrema. Change colors. Now every time there's a 1 output for cosine, secant also has the same thing because reciprocal of 1 is 1 and the reciprocal of negative 1 is negative 1. So it shares all the minimums and maximums. And then it just goes off to infinity like this. And this is the secant function. And that's it for secant and cosecant. Let's go ahead and graph some transformed cosecant and secant functions. Let's take the first one. Y equals positive 2 cosecant x plus pi over 4. Now what I like to do is actually graph this as if it were related to the sine. So what I do is I graph the related function, which is 2 sine x plus pi over 4. And then I just go through the same process I did when graphing the original parent cosecant function. So I note that the amplitude is 2. Right now I'm analyzing this. The b is multiplied by x, it's 1, which means that the period is 1 because the period is equal to 2 pi divided by b, which is 1. And our increment is going to be the same as the original function, so I'm not going to write that one. Now our c is negative pi over 4, but I'm going to go ahead and set the argument or the input of the angle equal to 0 and to 2 pi and solve both those equations. I know that the period for sine is 2 pi, so cosecant must be the same. Notice that this function is going to begin at pi over 4, negative pi over 4, and then I need to subtract pi over 4 from 2 pi. To do that, I've first got to convert this to have the same denominator. So 8 pi over 4 minus pi over 4. And that is 7 pi over 4. All right, so our beginning value is negative pi over 4, and our ending value is 7 pi over 4 for the first period. When I graph these, I go ahead and graph the original sine function, then I graph the cosecant. I don't try to hide the sine function or anything. I just go ahead and put it on the graph. Now this function is going to begin at negative pi over 4, and it's going to stop at 7 pi over 4. So I'm going to have to change my graph slightly. I left this so that it was possible for me to move it around. Let me go ahead and unsync this, move this over. Let's go to there. Sure. I just wanted to make sure I have plenty of a good viewing window. All right, I've got negative pi over 4. In fact, I'm going to go ahead and skip every 2 and just do by pi's over 2, just because it's a little cleaner on the screen. This is 6 pi over 4, and then I have 7 pi over 4 here. So I'm keeping that in mind as I graph. Now sine starts and stops. This is the picture I have in my head for sine. Sine starts and stops on the axis. But our starting point is at negative pi over 4, and it's going to stop at 7 pi over 4. Halfway between those values is going to cross those. And notice there's 8 tick marks between these two values. So I'm going to count 4 from this one. 1, 2, 3, 4. The quarter mark, it's going to be up on the amplitude. Now the amplitude is 2, so I'm going to go up 2. Same thing between the half mark and the end mark, I'm going to go down 2. That's the original sine function. And I could go ahead and draw that, but since my handwriting's so sloppy, I'm just going to leave the sine alone, and I'm just going to graph the cosecant function. First, change colors. Note that every time sine has 0, there's an asymptote. And then the extrema of sine are also the extrema of cosecant. Remembering that cosecant goes up instead of down because it's a reciprocal of sine. And then I just follow the same pattern. Note that there's 2 between here, so there's going to be 2 right here, and it's just going to go like this. And I've got 2 over here, so it's going to go over here like that. And that is this function. Let's go to the next example. Let's say we have y equals secant 2x. I like to graph the original cosine or sine function that goes with this one, and that would be cosine 2x. A is 1, C is 0, D is 0. This is very simple. It's just B equals 2, and the period is 2 pi divided by B, so this is 2 pi divided by 2, which is pi. Remember, the increment is a fourth of pi, so it's pi over 4. I'm going to count this by pi's over 4, but I'm going to skip every one just to make my graph a little cleaner. So pi over 2, pi, 3 pi over 2. Keeping in mind that my new period is pi. There is no phase shift, so there's no need to analyze the graph any further. All right, remember cosine starts and stops on the amplitude. So it starts here and it ends here. Remember the period is pi, so it's going to end at pi from 0. Halfway through it's at negative 1, and then we have these values. I'm going to go ahead and continue the graph so that it'll be easier when plotting the secant function. Every time cosine has a 0, every time cosine has a 0, there's going to be an asymptote for secant. And the extrema are the same between the two functions. So I can just go ahead and graph looks like I forgot a asymptote. And that is it for y equals secant 2x. Let's do just 2 more examples to make sure we're understanding graphing transformed secant and cosecant functions. Let's say we got a graph y equals 2 cosecant x plus pi over 2. Notice this is going to have a phase shift or horizontal translation. Let's analyze the original function that goes with cosecant, and that would be the sine function. So let's just graph the sine and then use that graph of sine to graph the cosecant function. Notice a is equal to 2, b is equal to 1, so the period is the same as the original sine function, so it's 2 pi, which tells us our increment is still pi over 2. And we have a c of negative pi over 4. But like I said, I like to take the input and set them equal to the original beginning and end. X plus pi over 4 is, pi over 2. And this shouldn't be pi over 4. Oh well. So pi over 2 is equal to 0, and x plus pi over 2 is equal to 2 pi. I'm going to go ahead and solve each of these. My new beginning value being negative pi over 2. I'm going to go ahead and convert this in my head. 2 pi with the denominator of 2 is 4 pi over 2. 4 pi over 2 minus pi over 2 is 3 pi over 2. All right, these are my beginning values. My increment is still pi over 2, using that when graphing. So I'm going to go and graph my original function, labeling my axes. I'm going to go ahead and label all the pi's over 2 because I think it'll help me to keep things consistent. All right. Remember, sine starts and stops on the axis. Sine starts and stops on the axis, but the new starting point is negative pi over 2. The new end point is 3 pi over 2. Halfway between those, it crosses the axis again, and then it goes up the amplitude. But the amplitude in this case is not 1, it's 2. All right, we go ahead and plot the rest of the points. All right, remembering that this is the reciprocal function, so we are dealing with where every time the zeros of sine, we have the intercepts, the asymptotes. All right, and the extrema are the same. So now I can just go ahead and graph my cosecant function. And that is y equals 2 cosecant x plus pi over 2. Stay alive, stay alive, stay alive.